Today we're going to talk about what's called logarithmic functions. And what logarithmic functions are, they are inverse functions of exponential functions. So it allows us to solve exponential equations using logs, kind of like how square roots would let us solve quadratic equations, and the square root is an inverse of a quadratic. So, like I said, inverse of an exponential function. Now, for exponential functions, remember we had f of x equals a to the x power, and our a value had to be greater than 0. We had to be raising a positive number to a power. So we must be positive. And again, that will allow us to solve logarithmic equations. So that we have to remember, though, that when we talk about inverses, that the domain of one of the original becomes the range of the inverse. So we got to keep that in mind when we talk about logarithmic functions, that it goes back to that these are inverses. And like I said, the inverse of an exponential is called a logarithmic function. Now, the definition of a logarithmic function is that if we have y equals log base a of x, then what is true is that x is equal a to the y power. So the way I like to think about that is that the log equals exponents. So if we have the word log here, then on the other side of the equal sign, this is our exponent. And then the a value here is our base. And then I call this the other number, or we can also call it the value. And then when we rewrite that in exponent form, this x, that's our value. A is still our base, and this y here is our exponent. So I also like to write it over here, so we have exponent form, and we have log form. So in exponent form, we have a base raised to a power, which is our exponent, and that just equals a value. We know that we can calculate that, and that would equal just a value. And then in log form, we have the word log, and we have the same base, which is written a little bit below the word log, and the value. And like I said, the log equals our exponent. So you're going to hear me say that a lot, that logs equal exponents. So we would read this as f of x equals log base a of x. It's a logarithmic function with a base a. Now, if we don't see a base written down, it's an invisible 10. It's called the common log. And we're going to see that a lot too. Log on your calculator, the log button on your calculator is really log base 10. And we always want to rewrite log base 10 as just log with no base written down. That's a more appropriate way to write it. And then the letter E is coming back here. So if we have a log base e, it's called the natural log, and we notate that as the ln of x. So instead of writing log base e of x, we are going to write the ln of x. And remember, these two forms, again, are equivalent. There's log form and there's exponent form. And as we said already a couple of times, the logarithm is an exponent. It equals the exponent of an exponential equation. So this means that log base a of x is the exponent to which a must be raised to obtain x. So you can think about it as this right here. For our base is a. So a raised to what power will give us that value here, x. If you think about it that way, when we can use the perfect squares, perfect cubes that we know in order to find out what that exponent is. So on the next page here, we're going to write the logarithmic equation in exponent form. So the way I like to do it is I always say, okay, what's my base? The base is a smaller number, 2. And then I know my exponent is on the other side of the equal sign. So whatever is on the opposite side of the word log is my exponent, 2 to the 5th power. And now that is going to equal that value, or I call the other number, the stuff I'm taking the log of, 32. And then we could verify with a calculator that 2 to the 5th power is equal to 32. All right, B, we got log with no base of 1 over 100 equals -2. Remember, if there's no base written down, it's an invisible 10. So then we take our base, 10, raised to the -2nd power equals the other stuff, 1 over 100. And we could verify that with the calculator as well. Okay, so remember, ln is log base e. So if it helps you to write this down like that, then you can easily convert and say, okay, e is my base, 0.0693 is my exponent, and that's going to equal the other number, 2. So then letter D, we have ln of the third root of e equals 1/3. So again, log base e of the third root of e equals 1/3. E to the 1/3 power is equal to the third root of e. Because remember, our base is e. Our exponent is what the log is equal to. And then the other number goes on the other side of the equal sign. And we know that the 1/3 power is the third root, just another way of writing it. So now we're going to go in the other direction. Write each exponential equation in logarithmic form. So for these, I just like to start with writing the word log and say, okay, what is my base? My base is 3. Okay, and logs equal exponents, so then I write an equal sign and say, okay, my exponent is 4. Well, then that means that the 81 must be my other number that goes with the log, the value. So we have log base 3 of 81 equals 4. So then letter B, start with the word log. Our base is 10. Our exponent is -4. And then the other number is 0.0001. Now, we said that we should not write log base 10 like this, so we're going to rewrite this as the common log of 0.0001 equals -4. And we can type that into the calculator to verify that it is correct. Because remember, if we just do on our calculators the log button, so log of 0.0001, that gives us -4. All right, so now we have e to the x equals 5. So we're going to rewrite this as the log base e, and then our exponent is x, and then our other number is 5. And then we're going to write that as log base e is the ln, so the natural log or ln of 5 equals x. Now, if you understand this and don't need to write log base e, then that's okay. You can skip that step. Like for letter D, it's okay. I have log base e of, or log base, cut. So like for letter D here, we have e to the 3/4 power. Well, I know that I'm going to have to take the, when I change this to log form, it's going to be log base e, which is the natural log. So I'm just going to start from that, from the get-go. Log base e, or ln. Our exponent is 3/4, so that's going to go by itself. And then this is my other number. And again, we could type that into our calculator. Now, it may not be exact, but ln of 2.1170, and we should get something really close to 3/4 or 0.75. I think we can agree that for our purposes, that's close. Right, now, down here, we're going to take this a step further and evaluate these logarithmic expressions without a calculator. So the first thing I like to do with these is set it equal to a variable, so equals x. Then we change it to exponent form, so 5 to the x power equals 1. Well, what if I raise something to a power and get 1, that means it must be 0, because anything to the 0 power is 1. So x is equal to 0 because 5 to the 0 power is 1. Now, letter B, again, let's set this equal to x. That way we have our 3 components. 4 to the x power equals 64. So what would I have to raise 4 to get 64? Well, 4 squared is 16. If I do 4 to the 3rd power, so 4 times 4 times 4, that is equal to 64. So that means x has to be 3. Now, another way you could have thought about this is to say, well, 64 is really 4 to the 3rd power. Rewrite it that way and say, well, since my bases are the same, my exponents must be the same as well. So either way works. Okay, so then we have 3 to the x power equals 1 over 81. So again, we want to think about it, say, okay, how do I get that 81? Well, 3 to the x equals 81 is 3 to the 4th power. Well, we don't have it exactly the same right now. We have 3 to the x in the left side in the numerator equals 1 over 3 to the 4th. So we want to bring that exponent up into the numerator. So 3 to the x equals 3 to the negative 4th because I'm taking this and bringing it upstairs. Well, now that my bases are the same, that means my exponents are the same as well. So x equals negative 4. So for this one, we have log base 4 of 4 to the 3rd. So our base is 4, so 4 to the x power equals 4, this whole thing, 4 to the 3rd power. Well, like I was talking about earlier, since our bases are the same, the exponents must be the same as well, so x equals 3. Now, I know for letter E, you say, well, it's a common log. Can I type that in the calculator? Yes, you can, but I am expecting you to be able to do these without a calculator. And if you had a different base other than 10, well, how would you do that? So I'm going to do this without a calculator. So we have 10 to the x power equals 0.01. Well, 0.01 is really 1 over 100th, because when you look at that and say, oh, that is 0.01 or 100th, if we're talking about place value. So then we know that 100 is 10 squared. And like we saw in letter C, we can now move that up and change it to 10 to the negative 2 power. So then x would equal negative 2. Right, then letter F, we have e to the x equals e to the first, just e. Well, e to the x equals e. That just means that, again, the exponents must be equal. Since we don't see an exponent there, there's an invisible 1, so x is equal to 1. And then lastly, we have, that invisible base 10, so 10 to the x power equals 1. And just like with letter A, anything to the 0 power is 1, so x is equal to 0. So looking back at some of these, we're able to identify or construct some properties of logarithms. So no matter what our base was, if our other number or that value is 1, so log base anything of 1, we had log base 5 of 1, x was 0. We had log base 10 of 1, x was also 0. So log base a of 1 of anything is going to be 0 because a to the 0 power is 1. Anything to the 0 power is 1. And alternatively, ln of 1 is going to be the same thing because e to the 0 power is 1. Now, log base a of a, that's going to always equal 1. Because if we were to switch that to exponent form, that would be a to the first power equals a. Well, the only way for that to equal is for the exponents to equal, so it'd be 1. Alternatively, ln of e is also equal to 1 because e to the 1 power is equal to e. Now, to generalize that, log base a of a to the x, that's just going to be x. Again, we have a of a. If one of those was different, then this property wouldn't be true. And this is true because if we switch this again to exponent form, it would be a to the x equals a to the x. So you might say, well, does that mean we can just cancel off the log and the a? They're technically not canceling, but if it helps you to think of it that way, then yes. And then we have, again, with ln of e to the x is going to be x because e to the x is equal to e to the x. And then finally, if we have two logs that are equal that have the same base, a and a, then the insides must be equal as well, x and y. Similarly, if we have the ln of x equals the ln of y, the insides must be equal as well. Just like how we had the exponent property where if the bases are the same, then the exponents have to be the same. Same thing with the logs. If the base of the logs are the same, then the insides of the logs must be the same as well. All right, so we're going to use those properties to simplify these expressions without a calculator. So e raised to the ln of 22 power, that is an exponential function because we have a base raised to a power. Yes, I know that the exponent also has a log in it, but this is an exponential, so we need to change it to log. So to change it to log, remember log base e is ln. So set this equal to x. So we have ln of x equals the exponent, which is, our exponent here is the ln of 22. Well, because they're both the natural logs on both sides, that means the insides must be equal, so x equals 22. Now, letter B, we have the natural log of e to the ln of e power. This is a log because we have, at first, a log of something, but then that something is raised to a power. So then we're going to rewrite this in exponent form. Remember, the natural log, or ln, is log base e. So e raised to the x power equals the other stuff, e times the natural log of e. Since our bases are both e, then we know x is equal to the natural log of e, which we know from up here is 1. So then x is going to equal 1 because the natural log of e is equal to 1. All right, then letter C. Letter C is nice because it's log base 7 of x equals log base 7 of 10 to the negative third. Because they're both base 7s, that means the insides must be equal. So x is equal to 10 to the negative third power. Now, letter D, we have 6 raised to the log base 6 of 36th power. So it is an exponential function because we have a number being raised to a power. So exponential, we're going to go to log. So set this equal to x. So then we're going to switch this to a log. So log base 6 of x equals my exponent, which is log base 6 of 36. Well, now that the bases are the same, base 6, that means x has to equal 36. And then with letter E, you could do letter E a couple of ways. I would do it as changing, at first we're going to ignore the 1/4 for now. I would change 16 to 4 squared. Because we know from our property right here that log base log base a of a to the x power is just going to equal that power. So I have log base 4 of 4 squared. So this part right here is just going to equal the exponent of 2. So we have 1/4 times 2, which is going to give us 2/4 or 1/2. So that's one way of doing it. Another way of doing it is switching it to exponent form and say, okay, we're going to ignore that 1/4 for a minute. So log base 4 of 16 equals x. So we have 4 to the x power equals 16. Well, x has got to equal 2 because 4 squared is 16. But then we have that 1/4 now. So 1/4 times 2 equals 1/2. I like the first way that I did it better, but you're free to do whatever you want. So converting between exponent and log form is super essential. So make sure that when you're doing your homework that you really pay attention and practice that, so that way you're a master at it. So thanks for watching. Make sure to like the video and subscribe.